If you do not parse queries, you are not building search, you are matching strings. This is the pattern you'll be able to implement by the end, which parses a user query and summarizes its structure. I'm Professor Pi, teaching search and IR with simple Python. Search sits between user intent and document matching. Raw keywords are fine for a demo, but real search needs structure. Users want phrases, field filters, boolean logic, and exclusions. Success means turning messy text into a predictable tree you can score and combine with an index. That makes ranking stable, explainable, and fast in production. At a high level, a query parser turns a string into a small abstract syntax tree. Think of a sentence like author : quoted name and tag : Python or -draft. The parser keeps quoted phrases as one unit, tags fields as constraints, and builds and, or, not relationships you can translate into scoring clauses. Strengths are clarity and deterministic behavior. Weaknesses are you must decide operator precedence and how to treat missing fields. We will build a practical parser with a lightweight parser library. It will tokenize words and phrases, add field filters, support Boolean operators and negation, and finally normalize the result into a clean tree you can use for scoring. This keeps the code incremental and easy to test. Now we start by extracting basic tokens and quoted phrases. This snippet extracts search terms and phrases cleanly with pyparsing. The variable word accepts alphanumeric tokens plus underscores and hyphens, which helps keep common search terms intact. The variable phrase captures anything inside double quotes as one unit, preserving multi-word phrases. The variable atom combines phrase or word, so either can match, and one or more builds a simple sequence parser. The variable q1 holds a small query where quotes group words. The call parseString returns an ordered list of matched tokens, which we convert to a Python list for display. The printed tokens show how quoted text stays together, which is essential for phrase search. Next, we add simple fielded filters so users can scope terms. This example augments the tokenizer to support field filters using pyparsing. The variable field matches a simple field name, and value reuses phrase or word, so scoped values can be single words or quoted phrases. The variable scoped detects the pattern field : value and, with a parse action, converts it into a compact tuple that clearly marks a field constraint. The variable atom is updated so regular tokens and scoped tokens can coexist. The variable q2 demonstrates two fields and a free token. Parsing returns a flat list where fielded components appear as tuples, which we filter for display. The printed tuples confirm fields are captured distinctly from free terms. Now we introduce Boolean operators so the parser understands logic. This code introduces Boolean operators with pyparsing's infix notation to build a real expression parser. The variables and or are case-insensitive keywords to match operators naturally in user queries. The variable expr is a forward-declared expression, so we can define precedence rules that refer back to Adam. The infix notation call sets the operator table with and binding tighter than or, producing a nested parse tree. The variable q3 mixes a phrase, a free term, and a field, joined with both operators. Parsing returns a tree-like structure in tree, and we count operators to summarize the structure. The printed counts verified both and or were recognized and structured. Next, we make negation work both as a word and as a leading dash. This snippet extends the grammar with negation, allowing both not and a leading minus. The variable not matches either the word not or the literal dash, making it flexible for typical search syntax. The infix notation table places negation above and or, so it binds to the nearest term or fielded term first. The variable q4 demonstrates both forms of negation with an and an or. After parsing, the variable t4 holds a nested structure where negated sub-expressions are grouped correctly. If you tighten precedence for and or relax it, you change which terms bind together. The printed count confirms that 2 negations were applied in the parse tree. Finally, we normalize the parse into a compact abstract tree suitable for scoring. This example turns the parsed expression into a clean, structured tree. The variable t holds the parsed result, and L is the top-level list representing the Boolean expression. The function AST is a compact recursive transformer. Tuples become field nodes. 3-item lists become binary operator nodes. 2-item lists become negation nodes, and everything else becomes a plain term. This normalization makes downstream scoring or translation easy, such as mapping to BM25 clauses. If you add more operators, extend the AST rules similarly. The printed JSON prefix shows the OR at the root with an AND on the left and a NOT subtree on the right, confirming a usable query tree. This toy pipeline maps to real projects by replacing the printed tree with code that generates clause weights. In production, you would feed the tree into your document scorer, map field nodes to different indexes, and run timing checks on typical queries. The small, deterministic AST makes caching and analytics straightforward. Recap. This parser turns free text into a structured query tree. Use it when you need reliable phrase handling, field constraints, and Boolean logic. Caveat. Operator precedence choices affect meaning and must match user expectation. Next step. Scale this exact pipeline by adding scoring hooks and evaluating on a bigger corpus. Then tune the Boolean precedence and phrase handling against real queries. If short, practical IR helps, subscribe and watch the IR videos.